Good evening, everyone. How's everyone doing tonight? It's cold. It's really cold. Well, good evening, and thank you so much for coming to the Saddlebrook Science Cafe. For those of you who don't know me, my name is Samantha Pierce. I'm the facilitator for this talk. So thank you so much for coming out tonight. I have a few quick announcements before we get into our talk. And we will be continuing with this series, Mysteries Revealed, Discoveries in Chemistry. Now, if you're new to the series, welcome, and if you are returning, then we only have 2 more talks after this, so just this one and then the one in March. So I'm sorry, 1 more talk. And And for those of you who are interested, I know we did fall on the same night as Tucson Botanical Garden Science Cafe. Everything is recorded, and I do upload them to our website. So on the brochure in the back table, it gives the information, and then if you go to the specific venue, it'll list the presenter, what they talked about, and then I put the video up as well. Likewise, if you wanted to see past series or past talks, they're all up on our YouTube channel, and we do cache those videos. So feel free to check those out whenever you guys are interested in. Just a reminder, we do have 4 other Science Cafe venues, and they will be hosting talks in April and in May. So we have Tumac Hill, Borderlands Brewings, Magpie, so our downtown Science Cafe, and then the newest one at Tucson Botanical Gardens. These are all free and for the public events. And how many of you have been keeping up with the College of Science lecture series? Good, good. Okay, perfect. So yes, we did have a week off this week, but next week we continue. So on February 12th, doors open at 6. The talk does start at 7. And if you aren't able to head over to campus, do know that we do live stream the videos, and then we save all of our recorded videos as well. Those brochures are on the back, and then the series is called Searching for Certainty. And the website is uascience.org. You can definitely check out the whole series thus far, and then past years and what other presenters have presented on. And how many of you will be here March 2nd and 3rd in Tucson? Or in Denver? Yay! Okay. So Tucson Festival of Books is going to be a little bit earlier this year to coincide with the move to University of Arizona spring break. So within that is Science City, and we definitely coordinate with all of our different tents. We have science cafes, much like this, all day, both days. So different times, they are listed on the website, and you do get more of a description as to who the presenter is, what time they're presenting, and what they're presenting on. It's going to be a fun event. It's free and for the public as well as you would get to experience the entire Festival of Books. And sweet, that's it. Just a reminder of the format. Our presenter is going to give his talk. Afterwards, he did say that he would be available for some Q&A. And then I'll go ahead and close it up, and we'll give the reminder for our next month's talk in March. And we'll go from there. So let me find my notes on the presenter, I apologize. Right, so tonight's presentation is Fighting Climate Change at the Molecular Level, and presenting is Dr. Thomas Gianetti. Dr. Gianetti was born in the south of France. He obtained his Bachelor's of Science and Master's of Science in Chemistry and Chemical Engineering from CPE, Lyon in 2009. After working in industry for a year at Johnson Matthey Catalyst, he moved to California. He completed his PhD at the University of California, Berkeley in 2014, and he started his work with the University of Arizona in 2017. His research program targets the synthesis of novel organometallic species that were limited design, including novel species. Don't worry, I'm excited to find out what that means too. One of Dr. Gianetti's favorite hobbies is to create different experiments for his kids around the house and ask them all these questions. He did mention to say that, needless to say, it creates a lot of mess. And he apologizes for his accent. He hopes that you'll be able to follow his talk. His daughter has to correct his pronunciation when he reads her bedtime stories. Please help me in welcoming Dr. Gianetti.
Good evening, thank you for being here tonight. So, as Sam said, my talk is going to be about fighting climate change at the molecular level. So first, let's talk about global warming and some facts. So some people say that global warming is just fiction. Some people say that climate change is not important because the climate has changed in the past, which in a sense that's true. Because if we look at this graph here, we can see the temperature variation of the surface temperature for the past million years. And we can see that this temperature changed drastically. So it's true that the climate has changed significantly over the few thousand hundred of years. But what people fail to mention is, first of all, at each drastic change that you see here, that led to massive extinction of life. So that's already a problem. The second thing that, yeah, right? So like, you know, and the second problem also is that people say, like, yes, the temperature has changed, but they forgot to mention the time scale at which it changes, right? So if you look at this, it seems very sharp and steep changes, but actually, if you look carefully, the fastest change that has been observed is about 4 to 7 degrees Celsius over a period of 5,000 years. Okay, and if you zoom on an area which seems pretty steep, is in fact like about like 20,000 years and rather flat, especially compared to what we're observing here. This is what has been happening over the past century. This like blue line here, and what we're stating at is an increase of temperature of 0.7 in just 1 century. Okay, and what's a little bit frightening is that according to certain model, in the best case scenario would be at this level here, which is still be quite an increase in temperature. But at the worst case scenario, which means that we don't do anything about global warming and climate change, we can reach up to like 6 degrees changes, or like between 2 and 6 degrees in like 100 years. Okay, so remember, the fastest observed over a period of 1 million years was like 4 to 7 degrees in 5,000 years. Okay, so this is kind of like problematic. Global warming, who's to blame? Okay, well, the first thing is, in my opinion, is our society and our politics. Okay, so clearly there is something wrong with the way that the priority of things are going. Climate change and global warming is our most important and most challenging problem that needs to be faced. And right now, like our policymakers do not put enough effort and time in it, and they talk too much, not enough action. I think that was well represented by this sculpture by Isaac Polo that you could find in the street of Berlin in 2011. And it's called Follow the Leaders, which is basically represent a politician talking about global warming, drowning in a bowl of water. I think it's pretty self-explanatory. The second problem, or the second thing we need to blame, is the kind of like a misinformation. There is this problem about people thinking that global warming means that it should be like hot and warm everywhere. Okay, and one striking scene that was seen in 2015 is one senator that I'm not going to name because it's not about politics, but one senator came to the Senate floor with a snowball in his hand and stated that because he has snow in his hand, he proves that global warming did not exist. Okay, I mean, it's funny, but it's scary too, right? So there's this kind of like misinformation and misunderstanding about global warming and climate change. It doesn't mean that we're not going to have cold days. It doesn't mean that the weather is just going to be hot all the time. It just means that it's going to be changing. And overall, on the global scale, the temperature is rising. Okay. Now let's focus a little bit of science. The main problem is greenhouse gases. Okay. I think like most of you have heard this term, and these are often methane, nitrous oxide, and CO2. And one problem that we're having is the reason why we think that mankind is actually the cause of like this increasing climate change is because if we look at the emission, the global emission of these greenhouse gases over a period of just like 2,000 years, we saw that it was relatively flat, which corresponded to this kind of like temperature plateau that we observed in the previous slide. And in the past century, we have this very strong emission due to the Industrial Revolution, where we started emitting at a very fast rate these greenhouse gases. So what is a greenhouse gas and what is a greenhouse effect? Basically, it's the same thing that if you stand to the sun behind a glass, it's going to get pretty frosty, it's going to get pretty hot. Because what happens is our atmosphere will act as this glass by passing through the visible light. Okay, this visible light is going to be absorbed by our surface and is going to be re-emitted in thermal radiation in infrared, and this infrared is going to be captured by the greenhouse gases. And that will result in a warming, an overall like a heating of the lower atmosphere. And what's important to note is our atmosphere is composed about 99.9% of gases that are non-greenhouse gases, meaning we have 78% of nitrogen, 21% of oxygen, and about 0.9% of argon, and it's only the residual 0.1% that are greenhouse gases, and that makes this effect of warming our atmosphere. And greenhouse gases is a good thing, in the sense that we just need to consider it as a balance, and that is known in astronomy as the Goldilocks principle, meaning that Venus, we know, is too hot, Mars is too cold, and Earth is the right temperature. And one of the reasons for that, they made some models that if you consider the location and the atmosphere, that the temperature, the surface temperature that you should see on Venus is about -45 degrees Fahrenheit. On Earth, it should be about -10, and on Mars, it should be about -67 Fahrenheit. The reality of it is each of these planets have greenhouse gases in their atmosphere, and that leads to the actual temperature that you observe. In the case of Venus, 98% of the atmosphere is composed of CO2, which is a greenhouse gas, and that results to this huge elevated temperature at the surface of Venus, which is 872 Fahrenheit. The little 1% here is what makes our planet cozy enough for the life to happen, which is great, right? Because now that we have an average surface temperature of 57 Fahrenheit. On the opposite, like Mars that have very little atmosphere and very little greenhouse gas, and therefore there is almost no changes and no effect here. So I say greenhouse effect is important, but the problem is when you actually start emitting too much and you start increasing the amount that you have, then like what we will observe is an increase in the temperature of our atmosphere. So what's the future? Well, unfortunately, as where we stand now, it's not very bright. So here we have an example of graphs that show over the past 500,000 years the change in temperature as a surface, and in blue, basically the concentration of CO2 in the atmosphere. And you can see a very clear correlation that when there is a high concentration of CO2 in the atmosphere, there's a higher temperature. When that concentration drops, you have a lower temperature. And the problem is this. That's where we are. That's what happened in the past century here. And this is a projection of what we expect in the next 40 years. So that's what's scary. We're not talking about centuries here. We're talking about like your children, your grandchildren, my children, my grandchildren are going to have to face this very, very important problem here. And another issue is that this doesn't even take into consideration the snowball effect that global warming and climate change can have. Being that as the temperature of the Earth increases, you start like melting the permafrost, which is known to be a huge reserve of greenhouse gases, especially methane. So as the temperature increases, the permafrost is going to melt, and we're going to start emitting even more greenhouse gases into the atmosphere. We have also the temperature that you have more evaporation happening, more water in the atmosphere, which is also a greenhouse gas. And then we have like challenging problems such as like deforestation, because we know that plants and trees are the one that could actually absorb the CO2 and reduce this amount in the atmosphere. Same as the acidification of the ocean, being that CO2, when it's absorbed in the water, it actually turns into an acid, and that increases the pH or like, result in acidity of the ocean, and that is what in turn like result in like the death of like many corals, for example, which are also known to absorb CO2 when they're here. So that's kind of like the snowball effect that we're going to have. It's like the more we're going to go down this road, the more problem we're going to have. And the temperature and the climate is not only what we are facing ocean rising, which if you look, there's about 45% of the population on Earth that live by the coast. That means that if the ocean rises, there's that many people who are going to basically facing migration, and we know that when migration happens, there is conflict. Also, we're going to have some meteorological events, such as cold fronts, stronger hurricanes, longer droughts, more heavy rain. That's going to affect our agriculture, which might lead to famines, and also several diseases. So as I say, the picture is not that pretty, and that's why there's definitely something that needs to be done at this point. So in terms of science, what can we do? Well, there's a lot of research going into trying to lower our emission, right? The first thing that we need to do is like try to like cut down how many greenhouse gases we emit into the atmosphere. And there's like one approach to that is using renewable energy. And there's a lot of research gone into energy storage, wind power, solar energy, bioenergy, and that's like a very big field, but that's not what I'm going to talk about today. I'd like to talk about a different topic, which is, well, can we start converting or using these greenhouse gases from the atmosphere and like turn them into something else, to start to kind of like lowering the amount, or simply having it directly from the source, and instead of emitting it into the atmosphere, like trap it at this point and convert it, chemically convert it to something more useful. Okay? So here are our bad boys. These are the greenhouse gases. So we have CO2, carbon dioxide, we have methane, CH4, we have some chlorofluorocarbons, such as trichlorofluoromethane right here. We have ozones, and we have nitrous oxides. So during this talk, I will focus later on mostly on nitrous oxide and CO2, and I'll explain why. But before we go into how we can convert these molecules, we need to understand the chemical reaction. So I'm going to have to like walk through you guys about chemical reactivity, and especially two important concepts, which is reaction profile will contain kinetics and thermodynamics. Okay. So here what we're looking at is we have some reactant on the left, let's say A and B that we want to react together. And on the right, we have a product. So what you can see here is basically, in this case, we're going to call that a thermodynamically favored reaction because the product is more stable than the reactant. Okay? So, and this here is the gain of this is the energy that is basically released going from A plus B to C. This is called exergonic reaction. And as I say, these are considered thermodynamically favored, which means that if you put A and B together, you expect C to happen. Okay? There's another type of reaction, which is the endergonic reaction, which is now the product is not lower in energy than the reactant, is higher, meaning that it's less stable, meaning that you're going to have to provide to the system that much energy to actually be able to form A and B. So these are thermodynamic consideration. Okay? But now there's something which is really, really important, is the kinetics. Okay? And the way you need to look at that is, imagine you are in a mountain and you want to go from one valley to the other. What you have to do is you have to climb over a mountain. Okay? And the higher the mountain is, the longer it's going to take, the more energy, the more effort you're going to have to put into going over and then rolling back down to the other valley. This is the same principle, okay? Which means that now this here is called an activation barrier, which is the energy that you have to provide, regardless of your reaction being thermodynamically favored or not. This is the energy that you have to provide to go over that barrier and then form the product. Okay? So often, the kinetics is what will make the reaction go fast or slow, and it will determine how much energy you have to provide in the system. And that can be very critical, because let's take a very simple example, a different allotrope of carbon. We have on the left graphite, right? And on the right we have diamonds. If we look at the thermodynamic of going from one allotrope to the other, we realize that diamond is more stable than the graphite, meaning that this reaction should be thermodynamically favored. So if you take graphite, it should go to diamond. But this doesn't happen, right? You don't have your pencil turning into diamond instantaneously. And this is because the activation barrier, now this mountain that you have to climb over, is huge. And that's why this doesn't happen. And the only way you can go over that enormous amount of energy required is you have to go to high pressure and high temperature, and that's why like diamonds often form in like geological events and volcanoes where you can reach this extreme temperature and pressure. Okay. So now that we are here and we understand both thermodynamic and kinetics aspect of a chemical reaction, we have to consider, what about our greenhouse gases? What are they? Well, it turns out that most of them are actually, some of them are thermodynamically stable, that means they don't want to react and do something, but some of them are, and the problem is their kinetics. They are kinetically inert, meaning that they have very high activation barrier. So as a chemist, if you want to go over that barrier, you have to see, well, either I basically put a lot of pressure and a lot of temperature in my system, and that will allow me to go over, but remember, we're trying to fight global warming here, so trying to basically heat really high and use a lot of energy is not going to be useful. So instead, an approach is like, well, can we lower the barrier? Can we make that barrier lower, such as this reaction happen at lower temperature, lower pressure, or simply faster? Well, this is possible, and this is the world of catalysis. Okay? So if we look at now this reaction profile, you see in blue you have a reaction which is without a catalyst. And now you see that if you add a substance which is called a catalyst, then you're going to have to observe a different reaction pathway, often more complicated. But the outcome is that you will have a much lower activation barrier. If we go back to our mountain and valley analogy, you're basically having the difference to climb over that mountain versus taking a car and going through a tunnel. Same principle. Okay, this is what catalysis is about, and this is what we try to do when we develop catalysts. So, as you can expect, catalysis is very important. 1/6 of all of the manufactured goods actually in our country are actually involved catalysis step at some point. The reason for that is because when you use a catalyst, you're going to lower the energy required, which will lower the cost. But also you can actually lower the time, which also lowers the cost. You're going to change the number of side products that you're going to have. You can make it with less waste, and therefore overall making this chemical process greener or feasible. As a case study, I took the synthesis of ibuprofen. We all know ibuprofen, Advil, right? We all have to know at some point. Here's the original synthesis, which doesn't involve any catalysis, right? It's this multiple-step process synthesis to arrive to the ibuprofen products. And you can see that along the way, there is a lot of waste product. Later on, it's been shown that if you use a catalyst, in this case a nickel for that step, and a palladium for that step, you can reduce this multi-step synthesis into 3 steps, which much less waste, much faster, higher conversion, higher selectivity. So, again, catalysis is very important, and that's the game I'm in. We can find catalysis in fine chemicals, health, molecular biology, basic chemicals, energy, environmental technology, new materials, and food. So, there's 5 types of catalysis, and bear with me here, I'm going to walk through with you. There's like biocatalysis, that's basically the catalysis and the reactions that are involved in your body and involved in nature and biology. And the way it works is you have an enzyme which has binding sites, it's going to be able to bind a substrate. And then you're going to have a catalytic site. And what happens is you're going to have the substrate and the enzyme binding to each other to form this enzyme-substrate complex. Then the active site plays a role and you do the reaction, and for example, keeps this bond, if that's what you're looking at. And then you have formation of the product and you regenerate the enzyme, which is a key component of catalysis and catalyst. The catalyst is something that is not used, it's not consumed during a reaction, meaning that once the reaction is done, the catalyst is regenerated and then started again and again and again. So that's one type of catalysis. We have another type of catalysis, which is heterogeneous catalysis. In this case, you have your catalyst, which is in one phase, and your reactant, which is in another one. Often it's a solid and liquid phase. So here we have another process. So we have our surface with our metal, and we have our reactant A and B and C. So this is going to involve several processes. We first have diffusion of the reactant to the layer of the surface. Then you're going to have piezo sorption. followed by chemoabsorption, sorry for the terms, but that's what they are. And then you have surface diffusion towards the active side, towards the metal that's going to do the catalysis. Then you have reaction. And again, this is where the metal and your catalyst come into play by like lowering this activation that we talked about. And then desorption, and finally diffusion out. Okay? So heterogeneous catalysis is heavily used in industry, especially because it's cheap, it's easy to separate because now you have a solid, your product is in a solution, so you can just do filtration, recover your catalyst, and go on and so forth. The problem is you have certain rate of limitations, so the diffusion is going to be one of them. And also the problem is you have very low selectivity, and you often don't know what happens at the surface. I won't go too much into detail with that, but long story short, there's good thing and bad thing about that. The third type of catalysis is homogeneous catalysis. So, in opposite of heterogeneous, in this case, both the catalyst and the reactant are in the same phase. So, for example, let's say in solution. So here we have a solution, we have our catalyst, we have our reactant. And now again, what's going to happen is you're going to have diffusion where the catalyst and the reactant are going to have to find each other. You're going to form an adduct, and then you're going to have reaction, forming the product, and diffusion back, leaving your catalyst alone and being able to turn it. In this case, it's basically the opposite as heterogeneous catalysis, but the advantage of heterogeneous catalysis was where now it's basically a disadvantage because it's hard to separate, it's hard to recover, they're usually expensive, but they have a high rate, they are robust, and also they are very selective and they often work at lower condition. So the last two types of catalysis is kind of like fell along with this. The difference is when you talk about heterogeneous catalysis and homogeneous catalysis, you assume that the energies that you're going to provide to your system is thermal. So you're basically going to use heat to help going over the activation barrier. Because even if the overall activation barrier is lower than uncatalyzed, there is still an activation barrier that you have to go over. In this case, it's mostly thermal, whereas in photocatalysis, you basically use light. And in electrocatalysis, you use electricity and electrons. But it's just like the different form of energy that you're going to use to go over that barrier. So now that you guys are experts in catalysis, we can go a little bit more in detail about what my group and what is my specific focus. So I'm involved mostly in homogeneous catalysis and looking at reactions that involve basic chemicals, and of course energy, hence the stock, and environmental technology also related to this. So, more specifically, we use homogeneous catalysts that involve transition metals. Okay? Here is a periodic table of the elements. I don't know if you're familiar with this, but here in the middle is where we have the so-called transition metal, and this is my playground here. That's where we play, that's what we kind of like look at. So this is a little bit counterintuitive, right? I said it's homogeneous, that means in solution, but then I talk about metal. You know, like metal, it doesn't really seem that it's going to go in solution. You don't see iron going into the water and vanishing and being dissolved. Well, the reason is because we trick a little bit the system by doing something that is called organometallic chemistry. So what we do when we talk about homogeneous catalysis with metal, we don't just use a piece of metal per se. We actually design that a complex in which we have an organic moiety, which is called a ligand, which is going to surround our metal. And that is going to allow us to basically tune certain property of the metal and do things that the metal alone could not be able to do. So what we have is a metallic backbone, and is surrounded with an organic moiety. You know the term what we have is a terminator, right? So yes, it's exactly what we do. We create terminator molecules that are going to be used hopefully to terminate greenhouse gases. So, but a more seriously approach here is this is what we do, and then we have open side where substrate can come in, Here's an example of the zirconium complex. You can see there is a metal as a mineral surrounded by a ligand. This is a catalyst which is used for polymerization. So what it means is now, like, by choosing and designing these ligands, you can actually affect and design the geometry, the coordination number, how many ligands you have, how bulky they are, how soluble your compound is going to be, how reactive, how selective. You can play this game by basically, it's like a puzzle, right? It's like, okay, which ligand is going to be the more appropriate for which reaction, and you basically play with this. Well, you have to make them too, which is sometimes challenging. So that's exactly what we do in my lab. We actually design catalysts, and our methodology is we start with a challenge. Then we think in terms of ligand design, what kind of ligand is going to be appropriate for what we are trying to do. And then we go to catalytic design, where we bind down to metal centers to form this ligand-metal complex that we talked about. Then we look at the reactivity to see if it's efficient or not. If it is efficient, we look at the mechanism, meaning that we try to understand how the catalyst is going to react with your reactant and how they're going to interact. Because if you understand how this works, then you can be like, okay, I see that my ligand is too big, or I see that my ligand is too small, or maybe I need the second one, maybe I need something charged, I need to increase the solubility, I need to lower the solubility, and you kind of like go around in this game until you actually pinpoint the perfect catalyst for the reaction you're trying to make. So, what are the challenges that we're looking at? Well, based on the beginning and the title of my talk, clearly it's going to be greenhouse gases molecule, such as CO2 and N2O. We look at all those things, but for today I thought I would just like focus on these two. So the first thing is CO2. So what can we do with CO2? Well, if you look at it, you actually realize that you can do a lot with CO2. It can actually be used as a block, as a kind of like starting block for many precursors that then are going to be used for polymers, for like pharmaceutical, and for like more processed chemicals. So the idea is that can we convert this CO2 into basically building block that will be used by chemical company. The problem here is, remember, activation barrier. This is sometimes thermodynamically disfavored, but sometimes is thermodynamically favored, but still has very high activation barrier. So you need a catalyst. Okay, that's the game we are in. Specifically, we're looking right now as converting CO2 to formic acid and form methanol. The idea here is if you convert CO2, then you can use that as an alternative fuel. That's not only you get rid of some of the CO2 in the atmosphere, but you can use that as energy, or you can use it as a storage. So there's a lot of study and a lot of work going on right now about hydrogen fuel cells using hydrogen as energy. The problem with that is the kind of like the demand when it happens. The problem is that you form H2, and then you don't really know what to do because you don't necessarily need it right away. So you need a way to store it and put it in a tank and compress it. It's not good. It's not safe. H2 is an explosive. H2O2 is what you use to send a rocket into space. Okay, so you don't want to have a tank of that in your backyard waiting to turn on the light, right? That doesn't make much sense. One way to do that is like, now can we use chemical reaction to store this H2, in this case, in CO2, and basically form into something which is actually much more benign, not dangerous, not explosive, and then like use it when you need it and have it with dehydrogenation. So in this case, you have this kind of like neutral circle, so you don't really get rid of CO2 per se because you use it as a storage, but you have to see that whatever energy you use using that fuel is something that you don't use burning like other fuels that will emit CO2. So usually what we do is we cheat a little bit. Okay, so either you start and you say, okay, I'm going to start from scratch and I'm going to think about what happened, or you basically look at the best chemist ever, nature. Been doing chemistry for billions of years. So nature have been like doing this. They know that it knows how to do it. Okay. And that is kind of like point to what I was to one thing is like right now in my field, the state of the art, and I'm not going to spend too much time on this, but the state of the art is like using the metal with the ligand, right? And you kind of like, this is how a catalyst goes around the catalytic cycle and form carbonate, and then release, formic acid, and release now your catalyst. What we try to propose is like, can we use now a different type of catalyst which has a bimetallic, so two metal adjacent to each other. And as I say, the rationale for that is because we look at nature. And if you look at how nature deals with CO2, one way is through this enzyme, which is a CODH enzyme. Remember, that's like from the beginning of our talk, it's going to be biocatalysis. That's what happened. If you look carefully, any enzymes that nature uses to do biocatalysis have activation, so the active site, and this active site actually involves metals and ligands. So they are just organometallic molecules embedded into an enzyme. So a lot of chemists kind of like do this biomimic. It's like, let's see what nature does and let's see if we can get inspired from that. And you can see that in this active site here, you have two metals, nickel and an iron. And it's been shown that into the reaction with CO2, there is this kind of like tandem reactivity where CO2 is going to be activated or is going to be reacted using both metals at the same time. So why don't we try to have a system that have two metals next to each other and try to activate CO2 the same way that nature does? So here's basically our idea and our proposal, and what we're working on is trying to make this metal ligand complexes, which has this metal-metal bond, in order to do this tandem reactivity and try to convert CO2 into further chemicals. So the ligands we work with are shown here. I can show you slides and slides of synthesis, but I don't think this is the point. I'm just going to show you one slide. So here's where you can start. We make this, and then we basically connect this unit. We make two of them, and that's allowed us to kind of like make this pocket where you're going to have this color here as something that can bind to a metal. And here's how it works. You're going to have a metal, and then you're going to put a second one, and because you have so many ways this ligand scaffold can attach to a metal, it will result into easily forming a bimetallic complexes. Okay? So that's what we do, and then we look at how can we use it for CO2 activation. The last thing I want to talk about is N2O activation. Okay? Why is N2O important? We all know about CO2, we all know about methane, but very little of us know about N2O, which is a problem. Because N2O is the third largest emitted greenhouse gases and is 300 times more powerful than CO2, meaning that 1 ton of N2O is as potent in terms of greenhouse gas effect as 300 tons of CO2. So this number here needs to be rationalized by its potency. And on top of that, N2O is also the largest ozone-depleting agent. So there's clearly a problem with N2Os that have been overlooked even in the chemical society. Here's where N2O comes from. It's true that there is about 65% of the N2O in the atmosphere, which is background, meaning that we have it's not our fault. It's been there before. But there is about 36% which is our fault. And the reason is that most of the N2O is produced through the denitrification of nitrates. When nature takes nitrates and convert it into the nitrogen cycle, it emits N2O. Where we come into play here is that nitrate is what you have in fertilizer. So now, because we have this intensive agriculture going on, we actually increase the level of nitrate in the soil, which in result in like about 1/3 of an enhancement of N2O emission. On top of that, N2O is also a byproduct of the synthesis of adipic acid, which is nylon, which is a precursor for nylon, as well as nitric acid, and some of them are emitted with fuel combustion. So the challenge with N2O here is, again, what we talked at the beginning. Going from N2O and H2 to N2 and water, or from N2O to N2 and O2 is actually thermodynamically favored, meaning that the reaction wants to occur. But the problem is you have this large activation barrier, and that's why if you want to do that, you need to go to high pressure and high temperature, and again, this is not viable, and it's not environmentally friendly. So what we are looking into is, can we use this organometallic species that I introduced to you earlier, so this metal surrounded with this ligand, or these terminator molecules, can we use this to react with N2O, strip N2O with this oxygen? Now you have N2, which is the 80% of our atmosphere, so this is not a problem. And now you use this oxygen to make a chemical reaction. So this is a kind of like two birds, one stone. Is not only you get rid of N2 on one side of the cycle, but also you actually form something valuable and important. So once again, we turn to nature. There is one enzyme, there is many enzymes, but at least one of them, which is nitrogenase, which is known to convert N2O to N2 and water in the presence of proton and electrons. It's also the enzyme which basically is known to convert N2 to ammonia, but that's another subject. It's interesting to show that this is also an enzyme that actually converts CO2 to something else. But what is important here is if you look at the active site, so again, like the metallic or the organometallic related piece of that enzyme, you can see this scaffold here where the most important part of this active site is this ion, so you have the metal, interacting with the carbon. And it's been stated that this is like a positive carbon. So now you have, it's believed that like, this reaction is mostly driven by the fact that you have this ion interaction with something which is a positive carbon. So what we decide to do is like, can we synthesize molecules that do have a positive carbon? And that's what we're doing in the lab. We're making this ligand, so the organic moiety, part of these organometallic complexes, and they have now carbocation or positively charged carbon in it. And the goal is, of course, to then bind it to the metals, make this complex that we talked about earlier, and finally using that interaction, which is now this mimic with what we observe in nature, to actually activate N2O, make N2, and then use this oxygen to form chemicals. So, and here are the breadth of ligand that we're looking at. This is kind of like the overall or little snapshot of what we're doing in the lab and how we're doing. I didn't want to go too in detail with the chemistry here, but I'll be happy to answer questions after the talk. So I'd like to finish this presentation with kind of like stepping back a little bit and kind of like give you a take-home message of what can we do about this, because it's one thing to look at it in kind of like science and what scientists can do, but I think this is the responsibility of every citizen or every people living on Earth. So first we need to kind of like convince our politics one way or another, regardless of the party, regardless of the certain idea, that this is important. We have to come together and we have to fix this issue. We have to prioritize, we have to pass law and be who's going to help future generations to not face a catastrophic outcome that we're going to. That's one thing. The second thing is like ourselves. We cannot just say like, okay, it's your fault, it's everybody's fault. Okay, we are all responsible, we all have a carbon footprint. Meaning that if you look at the emission per sector, here's the residential. Okay? Meaning that this is like people at home. That is a lot. That means that, you know, like, it would be nice if people thought to think about turning off lights, you know? Maybe like not blasting the AC because or the heater too long. Maybe like not, you know, depending what kind of car you drive. I mean, I'm a little bit ideal and a dreamer, but that would be kind of like our generation, the young generation, my generation, your generation, every generation, to kind of like being aware of that we all have an impact. And at this point, we are so far in that every little step, every little thing counts. And the last thing is, of course, fighting this misinformation and looking at the education that we talk about, and that's an initiative that I'm starting at the university. I created a class, and I'm developing it in collaboration with a colleague, which is at the School of Law, where we basically created this class which will be offered to law major and science major, and try to have these two different fields coming together and discussing already at this point, because that's going to be the generation of scientists and the generation of lawmakers that are going to matter in 20 or 30 years. So we want to already now try to teach them how to interact with each other, how to learn and discuss with each other. And that is kind of the point of this class that we're trying to develop. So with that, I'd like to thank you for your attention, but also my group members, present and past. I'd like to thank funding, which we need to make any type of science. I'd like to thank my advisor. I'm still at the early stage of my career where I still want to acknowledge the importance of my advisor throughout my early career. I'd like to thank my wife and my kids who put up with me and they are supportive of what I do. And I will say thank you for your attention, and I take any questions. Yeah. So there's a mic here, or I can come to you. Or... That's fine. Yeah, I guess not. Yeah. Can I do that? Terminator. Yeah.
Is it on? No.
This one's on.
So you develop these Terminator products. How do you industrialize that where they're out in the atmosphere to get rid of the CO2 or N2O?
So that's actually a very good question, because so that kind of now you enter another field of chemistry, which is gas sequestration. So there's a lot of people, a lot of groups that actually work onto how to capture these gases from the atmosphere and try to combine them, right? And to put them in a way, almost put them in a vial, I can use my little Terminator and convert them. That's one way. The other way is, if you look at a power plant that already emits these gases, you could easily imagine that instead of having this pipe blowing the gas into the atmosphere, having this pipe linking to a plant which is next door, using one of these Terminator molecules and converting it. So it's not about just trying to trap what's in the atmosphere. It's instead of releasing more, it's you trap that before releasing it. Does that answer your question?
If you trap that material first with atmospheric material take care of itself over time.
So if you trap the CO2?
If you trap the CO2, say, coming out of a factory, will the chemicals that are already in the atmosphere, will they take care of themselves eventually, or is that just a second problem to deal with? So
you mean the CO2 in the atmosphere, if we basically just stop emitting anything, right, what's in the atmosphere? Yeah, I mean, it will take care of itself, but now we're talking about the lifetime. Basically, we're talking about this activation barrier, how high it is. And it turns out that CO2 is about, a couple of thousand years resistant in the atmosphere. N2O live about 100 years in the atmosphere. CO2 is about 1,000 years. So it will take care of itself, but you won't be there. So we cannot wait for this. But it's a great question. That's why I make this point about talking about activation barrier, and because reaction will occur by itself. It's just if this mountain is too high to climb, it's just going to take thousands and thousands of years. Yeah.
Is there any work being done on around the photosynthesis molecules?
Yeah, definitely. And that's kind of fortunately, there's there's a lot of work done, and that's this part of like photocatalysis. Yes, there's a lot of work where actually people use mostly heterogeneous material, and they kind of like put catalysts on the surface, and they use light to try to drive that and basically do what like plant does, like in photosynthesis manner. But again, you know, nature had 2 to 3 billion years to solve this problem. We're running out of time, but there's a lot going on. It's not my specificity. I'm not specialized in that, but there's definitely a lot of work. Yeah.
Right now, we're using a lot of platinum. What metals are showing promise for your platinum?
So this is an important thing that I didn't want to mention, but it's true that, so here I show you the transition metal. And we're facing another problem, that a lot of the thing we use right now is platinum, palladium, rhodium, sometimes gold, and this is also called like precious metal, meaning that there's non-abundant, there's not much on it on Earth. Because of that, they are really expensive. Because of that, we're going to run out of them very soon. So there is a very strong driving force to go toward the first row transition metals, the most abundant one, which basically is all the way to nickel. And the reason why this is abundant is because into a stellar furnace, or in the sun, or in a star is able to make, not our sun, but some stars are able to make all the way element all the way to cobalt. Anything which is happened, which is after, has been created during a supernova and an explosion. And these are like much more rare events, and because of that, the further you go, then the rarer the elements are. But did I answer your question? I kind of like drift away. So, okay, so what we want to target, what we want to use is basically iron, cobalt, and nickel. That's what we want to use. Unfortunately, as I said, we are at this early stage that we don't even know if the ligand are appropriate to what we want to do, right? And that the organomoiety bit. So like what we're doing right now is we use the efficient one to see is the ligand good, right? And once we've proved that, we're going to be okay. Can we back that up and use like some much more interesting and more abundant iron, nickel, and cobalt? Yeah.
Do you find computer models helpful in predicting what metals?
Yeah, definitely. So GFT calculations, so computer modeling, is really helpful, especially when you start thinking into this term here. Because when you design, and I want to put it on this slide, you can see that here I put a lot of possibility. I left the kind of like, but it's true that we use actually computer model to see what kind of group here, like how big they are, because if they are too big, then you're going to prevent coordination. So yeah, we do rely a lot on this. We also rely on it once it's formed in React to try to understand what the reaction will do. So it's kind of like, you know, it's a dance. We use experiment and computation.
Are the products you create with catalysis, are they themselves pollutant or are they useful?
Well, the reaction we target are not pollutant, and we target things that are useful. So, for example, in this case, as I say, what we're targeting here is basically things that, for example, can be used as a fuel. In the case of the N2O chemistry, this step here is called oxidation, and this is the step which is used a lot in pharmaceutical products. So you can imagine, like, you know, like agrochemical product, everything that have an oxidation step. If you can actually use this methodology instead of what we use now, which is mostly like hydrogen peroxide, which also generate a lot of waste, which are not really green transformation. So yeah, so we're trying to target not only getting rid of the greenhouse gas, but also doing something useful. Because I agree with you, you don't want to like get rid of one trash by creating another one. So yeah, that's a point.
Are the gases from animals for production of meat and things like that something you get involved with? And what solutions do you have there?
So you mean like methane? Yeah, so I mean most of the methane which is emitted, which is about like, it's a lot, it's still a lot. I have the slide at the very beginning in terms of numbers. I personally don't eat red meat that much. That's kind of like my personal way to do it, but that's, yeah, it's a little bit difficult. But there is a lot of research going into trying to do activation of methane, to go from methane to methanol, where you basically cleave this carbon-hydrogen bond in your CH4, and you make a CH3OH, right? And that's where, for example, N2O come into play, because you have to do this oxidation. So yeah, in the terms of like chemistry or in the chemical base, there's like study done to try to convert methane. But again, the emission itself. But as I said, like, methane is mostly come from agriculture and animals, and that is, it's about, it's I don't know, this is like more part per million, but it's about several like million tons. So it's, so I think like CO2 is like, I had this number, should I put it down? Like CO2 is like 36 million tons, and methane is about like 8. So it's still a lot. Did I answer your question?
Is there any way that we can address the countries that are like India and China, which produce a tremendous amount of our pollutants that we have no control over?
Yeah, I mean that's why it is a problem. I mean, right now I agree with you. I didn't put this chart on, but right now China is the largest CO2 emitter. It's China, then it's like us, and then it's Europe. So I agree with you. There's little thing we can do about that. Hopefully, they have people there like us trying to convince their politics and then the higher level of governance that they need to change that. But yeah, it's a problem. Okay.
Earlier in your presentation, I'm wondering your part of CO2 versus temperature.
Yeah. Do it again?
No, it's the one I think the other.
This one?
It's, looks like a million years and shows CO2 versus this is super.
Well, so this one is just temperature, and it's a million year, and then the next one is just half a million year, and it has like this. Yeah, this is a temperature. I'm not sure I understand. Yeah.
You've got 48 signal right there, two islands, separated by roughly.
Mm-hmm. Well, that's a very good question. I don't know. And I'm afraid I'm not going to be the one doing it unless I will speculate. But I mean, it's, you know, it's like the climate is like a clock, right? It seems that it is repetitive and there is like a pattern, and this is only 1 million years. And if we go back to 100 million years, it might be this cycle. And there is no critics about the fact that we are in one of this new 90 like cycle going down, right? But the problem is, and what is scary is like, you know, like this was true for the CO2. So when this kind of like drop happened, is because what happened is that the CO2 emission was very large, and over a period of like thousands and thousands of years, like planets, like Earth, like fighting that and starting absorbing CO2 through more photosynthesis and things like that. right? The problem is like, we are here, we came here, and like we decided to cut most of our forest, so we cannot, the Earth cannot absorb all of this extra CO2, and on top of that, we decided to like put even more CO2 in the atmosphere. So we are like kind of like perturbing this natural cycle, and that's the fear that most of scientists have, is like, we convinced that it's not going to go back down because this. So well, that's kind of like what go back to the beginning, where you have to be careful because it does look sharp, but if you actually zoom in over a period of like 20,000 years, this part here is what you see here. It's not that sharp. It's not that there is like one very specific event. The only actually specific event is what we are doing now. But everything here, because it's on such a large scale, if you actually zoom in onto it on something which is more decent, or like human, or like, I say, mining related to 20. Exactly. Even though it looks chaotic, it looks very still. That's fair.
I just wondered if you'd ever wandered in that area.
I have not, because I am not a climate scientist, so, but I agree with you. I mean, this is definitely a question. Also, I mean, these are models and data, so it has to be taken with some, but I don't know, it's pretty convincing to me. Yep.
I wanted to mention in response to the China and India, there is a bill that was just dropped into the House of Representatives that would put a price on CO2 emissions, and that would be on goods produced in the United States and imported into the United States. Economic modeling shows that it will drop CO2 emissions by about 31% in 12 years. That's HR 763, if anybody wants to write their congressman and ask them to support it.
Thank you. I mean, that's where, that's kind of like where this brought on. It's like when something seems to be, that it will do an impact, and it's that it's dropped or debated over issues. You guys have a lot of questions.
For how many years have people been working in your area of study?
Excuse me?
For how many years have people been working in your area of study? Is this something that's going on for generations, decades?
So, organometallic, so homogeneous catalysis, I would say that the birth of organometallic chemistry is with Sir Wilkinson, which is about 1950s. So that's where catalysis in the homogeneous model started. People starting to look at CO2 activation and greenhouse gas activation, that's about like 2 to 3 decades, I would say, since like the first initial report. Yeah.
I did a chart with, this shows the temperature and the CO2. Do we know? There's the high ones, and then it goes down. Do we know what the Earth did, because we weren't here yet, to make it go down?
So that's kind of like correlates to the question with the gentleman in front. Like, I personally don't know. Yeah. I mean, there's probably like speculation and model, but it's hard to know what happened, like how did this happen, but it's an ecosystem, so I feel that plants feed on CO2, so you can imagine that as long as there's nobody there to perturb that, an increase of the CO2 will increase the proliferation and the growth of plant, and in return they're going to basically absorb that significantly, and over a period of, because as I'm saying, people are talking about over a period like 50,000 years, right? It doesn't happen like this. Then this increase of vegetation then counterbalance this high of CO2 and then drop down. And then when you're down, then there's less CO2, so plants doesn't grow as fast, and therefore you start emitting more CO2 through volcanic effect. But again, this is very speculative. That's going to be kind of like guess.
Any other questions? All right, thank you so much, Dr. Gianetti. Just as a friendly reminder, the next Science Cafe is Thursday, March 14th with Dr. Victor Hubry. He's going to be presenting the chemistry of human behavior. Thank you, everyone. Enjoy your evening.
My Prius.
Save the planet.
Basically, what he said was at the end, you know, when he couldn't answer that question, I really don't know. Talk about the cyclical. That's basically what he was saying.
Well, look at that.
Right.
What does that say? Cyclical highs and lows.
Yeah, but what he did say when he run that chart is that it gradually has gone, the highs are gradually going higher. Which
Well, and then that last bit. Yeah, I mean, you know what? I'm not an expert. I hear both pros and cons. The way I look at it is, it couldn't hurt to, you know, try and do some of these things, solar and wind and recycling and whatever. It can't hurt anything, whether it's going to actually make a dent and move the needle at all. I mean,
well, I look at it a little different. The problem we got politically is that every time you want to do something, it costs.